about sequential data analysis. The So my flow of the slides will be like this, that I will give you some preliminaries of sequential data analysis. Then I will talk about vector autoregressive process. You can imagine that bring it to scalar autoregressive process easily. Then recursive neural networks. And I will not talk about probabilistic formulations on HMM. If I finish before my time, then I will have a gap. And if I have time, then I will talk about HMM. Okay. So preliminaries of sequential data analysis. So preliminaries of sequential data analysis. Sequential data analysis are mainly two types. Typically time domain and space domain, but of course you can use other domains if you have access to that. So examples of some few typical tasks for the for the time domain or space domain sequential data analysis is tracking the signal over time or space. For example, I'm just giving a very arbitrary example, like let's say there is a missile which is launched and you would like to know at a current point at a particular time what is going to be the missile coordinates after certain time, like let's say after few milliseconds. Okay. Then prediction of signals or parameters. For example, I have given a case, so I'm showing you different examples. This is a channel condition. Channel condition means what? Let's say that your phone is connected with the base station. Your mobile is connected with the base station. So base station is sending some information and your phone is capturing it. So within the base station and your phone, there is a channel. This is the wireless channel, and all your wireless communication basically uses this kind of wireless channel. And the channel changes over time. For example, let's say, the day is extremely hot. Maybe then the channel got changed, or the day is very humid. The channel got changed. There is a car or a tree, or some obstacle in between, even inside the room. So the channel got changed. So you need to know this channel. Otherwise, you cannot transmit the information. So in that case, you have to have an idea what your expected channel should be. So you have to track or you have to predict the parameters of that channel over the time. Okay, otherwise you cannot design the system. Even you cannot transmit any information. Then third one, let's say data imputation. For example, let's say that I have an image, and within this image, some pixels are off. That means the sensors cannot, somehow could not collect or measure those pixels. So you would like to basically impute those pixels. This is called missing samples. And you would like to interpolate and fix those missing samples. Then, and this can be over a sequence. For example, I have a sequential data and some of the data is in a time series maybe missing, and then again the data continues. So how do I impute that data and see the time series? Then classification using sequence data. For example, I have given another example, maybe automatic speech recognition. So speech, we mostly use to communicate between ourselves, and that's the time series. If you collect the speech signal, it's a time series, and from this series, a machine has to understand what is spoken. That means which are the words and what kind of words it is, and then form the sentence and finding out the meaning of it. Then comes estimation. For example, let's say there is a noisy sequence. You have a true time series, but you are not being able to see the true time series, but you are seeing its noisy version. And then from the noisy version, you have to estimate what is the true time series. Okay. So that's also, that is an estimation problem. So you can see that, I have written in the left side, this kind of general inference problems like tracking, prediction, data imputation, classification, estimation. So in the machine learning field or statistical signal processing field, in this way, there are something like 5, 6, standard inference task, and most of your practical problems will fit in those scenarios. Okay. Now, for my slides, I will always consider discrete time domain signal. Okay, with respect to a sampling. I'm not considering right now a continuous time domain signal because that treatment is a little bit different. Conceptually maybe same, but still a little bit different. And this is also for the spatial domain. That means in the space, I'm not considering continuous space, but coordinate wise, like pixel wise in case of an image. Okay, so that's the discretized system. So please note that there will be difference between the discrete system and the continuous system. Okay, and you must have to know this one before applying your algorithms or the thought process. Otherwise, you may do completely wrong things. Now let's track a time series signal. So this is a time series. It is actually a discrete time series, but I'm showing it in its continuous mode. So every points are interpolated, given connected by maybe a straight line. Okay. So in this way you are seeing it. So for example, this is an euro versus Swedish krona, conversion change over 90 days. And here I have written August 22 to November 21. So, by €1, you get at this point of time, maybe 10.40 was the Swedish krona conversion. Then it fall, and then it again increase. Okay. So you can see that at this point of time, euro is more stronger than krona, and sometimes euro is weaker with respect to krona. Okay. And this is a very interesting time series because lots of financial transaction is actually done on this time series. Okay, if somebody can predict that what is going to happen, in future. So in that case, you will convert. You will basically buy which kind of currency you want to. So if it's euro is weaker at certain point of time, possibly you want to buy it, but you don't want to sell it. Okay, so in this way it works. Now, if this is the time series, then I can have different kinds of prediction problems. One standard prediction is that what will happen tomorrow? Okay, what is the price I can expect? The same problem I can say that what will happen after 7 days. Okay. And you can easily understand that the problem of predicting the after 7 days should be harder than the prediction of 1 day. Okay. But in certain cases, if the data has a periodicity, some kind of correlations between, some kind of correlations with respect to certain periods, then it may be easier to predict what will happen after 7 days than what will happen tomorrow. Okay, it can happen. And according to that, you have to design your algorithms. Now, here I have shown you one-dimensional sequence. You can treat this one-dimensional sequence directly and predict it. But there are ways in signal processing to see this time series and trying to find out its time varying properties. What is this time varying properties? I will come in a very easy way. But if you know that the signal is not completely stationary over time, but it varies over time, then there are other tools to handle it from the one-dimensional signal. So this is called, let's say, in this case, I told you 1D sequence signal to 2D sequence signals, but you can have multiple dimensions. Okay, so for example, I can have a multiple dimensional signal, sequential signal, to multiple dimensional visualization of the sequential signal. Okay, so this can happen. Here I'm just showing you 1D sequence to 2D sequence as a visualization tool. Okay. So if you see here, all of you possibly can see my cursor. If you see here, this is a speech signal for something like maybe close to 3 seconds long. Okay, so somebody spoken some sentence and it is collected. Okay. If you zoom in, you can even see that, a nice time sequence actually. But now by seeing this signal, it is very difficult to interpret this signal. It's just a one-dimensional sequence. Then in the speech signal processing community or audio processing community, I mean, what they think like this. Well, if this is one kind of sound, let's say this is O and this is PO. Okay, so these two are two different sounds. For that, the frequency contents are different. Okay, and due to the modulations of speech in our generations of the speech through our speech production system for humans, this modulation changes, and that's why every sounds becomes distinct and different, and that we basically can perceive, right, through our ear, through our listening. So now what you do, there is a tool called short time Fourier transform. The short time Fourier transform is a small window that you think it like, okay, I have a small window, and for small portion I would like to find out what is the frequency component of that. So it's nothing but a spectrum of a short window. Okay, so let's say this is the picture is, so you have to understand the meaning of this picture. In this side, this is the same time scale, okay, in the x-axis, but in the y-axis, what I have here basically I calculate a small portions window, and then again shift that one, again a small portion window, then again a small window, like this. These windows are shifted, and for every window you compute the power spectrum, and that power spectrum is with respect to frequency. Their amplitude is with respect to frequency, the amplitude is plotted in the z direction, means perpendicular to your computer screen, and that values are here. So that means more red means your higher amplitude of the frequencies, blue means it is low amplitude of the low frequency component. So you can easily see that, for example, here, this is the frequency components, these are the frequency components, and you can see that, in case of speech, there are some frequency bands, okay, on which the speech signal is energy is concentrated. These bands, even in the speech and audio processing society, called formats, and we have, as a human, we have kind of an idea where are the most frequency components are there, and according to that our ear also listens. Yes, please. Okay, so wavelet transform also you can do. That is also a time frequency analysis. This is an easier time frequency analysis. Okay, but this is that window wise. So this is the picture. These pictures people came in 1950s, 60s, and that point of time the idea was that if a computer can read these pictures, because every sound has a distinct image. Okay, so you see that from the time domain sequence, I now have brought up everything in the image domain, right? And every image for a particular portion, particular sound like ah is very similar across people, okay, across different age groups and genders. So if we can do then image processing on that, then we can design a speech recognition system. That point of time, there was some thought process like this, but finally it did not happen. But finally people used other kinds of methods. But you can easily see from this picture that these pictures gives you some explanations or interpretability of this time domain signal, raw signal, that which you are seeing here. Because from the time domain raw signal, you really cannot understand much, except there are some parts of activities. But now in the frequency domain, you can figure it out. For example, when I see here, see that this portion here, it is much more periodic, and then this is very, very noisy, right? And then again it is more periodic if you zoom in. So you see that when this is much more periodic, I have low pass low frequency components which are more prominent. But when this is much more noisy, it is a high frequency component. That exactly I should think, right? I mean, it matches with my standard signal processing knowledge. And then again it goes back here. And because of this change, only that different kinds of sounds we can perceive. Got it? Okay. Now, using this above speech signal example, let's say we can visualize many types of problems, and let us visualize some problems. And once you see, because this is the data you have, this is some kind of transformation you did for a better understanding of the data, and from this data, what kind of problems you can think of? Yes.
One of the questions is that, like, how do you they decide the time window for this like signal processing?
Okay, so what is the window length possibly that you are asking, and what kind of windows we will use? Okay, so there is some fundamental quantities called time frequency bandwidth. So the general idea is this, that if you have higher time resolution, then your frequency resolution is poor. If your frequency resolution is high, then the time resolution is poor. Okay, this is well known. It's some kind of Heisenberg's principle. Okay, so there are some ways to find out it optimally in certain cases. But most of the times you do little bit of experiment and use your domain knowledge to fix this time window length. And generally we use tapered windows. One of the standard windows is Hanning, this Bartlett, this kind of windows exist. Lots of research is done, and the windows are chosen in such a manner such that the leakage of the power spectrum is low in its side lobes. But maybe this is too technical to make you understand, but it's some kind of tapered window, and these windows exist actually. You can simply call the windows and use it in your program. Okay. Now I have this one with me. What kind of problems I can think of? Okay, let's say this was sound 1, this was sound 2, and this is sound 3. Let's say, okay, this portion is sound 1, sound 2, sound 3. Say, let us assume a case. I don't know whether I did not map with respect to the true speech, but let us assume a case where the signal has portions from 3 speech sounds. Say this portion is A, this portion is E, and this portion is O. Okay, so these are the 3 distinct events, A, E, O. What kind of inference problems I can have? Given a signal portion, what sound is it? For example, I give you this portion and then ask what sound is it? So you have to find out this is E. That's a classification problem. Okay. Second, given a signal portion, what is the next likely sound? For example, I give you this one, let's say A. You have to predict the next one should be E or O. Okay, so that's a prediction problem. Even in the sound domain means, so I'm not now predicting the values of the time series. I'm just trying to predict what is the sound event. Okay, given an event. 3. Given a noisy signal portion, what is the true signal? For example, let's say this signal, somehow you got a noisy signal and you would like to find out what is the true signal. That's an estimation problem. That exactly, I told you. Now you can see in a better manner. For signal, if this signal is corrupted by a high frequency noise, so in this domain, what will you see? You will see much more high frequency noise here, right? But you know that the speech signal typically should not have too much high frequency signal, right? So you can filter this portion from here and reconstruct it back to the time domain signal. Okay, but how do you know that the high frequency signal exists or low frequency signal exists? So from here you go to this domain, you visualize, then you use your domain knowledge that the speech signal should not have too much high frequency signal, and you filter it out and come back to the audience signal. Got it? The how to do the estimation problem. Then given a signal portion like this or this, these are, if you check this one, for example, if this is a 16 kilohertz speech signal, so for 1 second you get 16,000 samples, discrete samples. You cannot really work with 16,000 discrete samples, and please note that, today's speech recognition systems are, collect data over millions of people and, many hours. So you really cannot collect, those many samples and then design some systems. That's too much. But that's why, you have to collect you have to parameterize this signal in such a manner such that the most important information exist in those parameters, and those parameters you use for a certain task. That is called feature extraction problem in our machine learning terminology. So given a signal portion, what is the essence of it? That is the feature extraction problem. Okay, so you basically figure it out, where is my information lying, how to represent that signal such that my task, such that that can be useful for my task. And please note that task can be different. For example, classification is one task, prediction is one task. So finding a feature vector for classification task may not be so use it for the prediction problem. It can happen. Okay. Then comes a very interesting problem. Actually, this exists in all your mobile phones. Is that given a noisy signal portion, because this is noisy now, is there any speech signal? This is called detection problem. That means, given a noisy signal, you really don't know whether the noise has buried the true signal or there is no true signal exist for that portion. Okay. And if you think that, okay, there is a true signal, if you think and then use the noisy signal for some inference task, actually you're doing wrong things, right? Because the signal even does not exist there. So you must have to know whether there is something true signal exists. This is a detection of the true signal. Actually, in your phone, this is called voice activity detector. Okay, VAD in our terminology. What it does, it like this, it like this, let's say this is my speech signal. These portions are the silences. You know that for the speech, silence is very important. If we for example, in a standard speech signal, at least 30 to 40% is silence in a spoken verses. If the silences are not there, then all the words will be mixed. We cannot even understand which word is what. Okay, but silence means I don't have to code this portion and send it through the channel, right, to your mobile phone. I just have to tell that, okay, there exists a silence for this many microseconds. That's it. I don't have to code all the values of the silence, because silence are almost zeros, right? I mean, there is no need to code them and send it to the other side of the channel, because you are simply losing channel bits or your information resource over the channel. Because that point of time, somebody else can use the channel and can talk. That's called multiplexing of the channel. And that's why that today in a same mobile communication region, we can cater to several speakers, because we know all the speakers, even though they talk, they are, spoken portions will not align with each other because they are independent talkers. Okay. So this is called a detection problem. Okay, hope that you understood several kinds of problems, what we can think by seeing one kind of observation. Now comes situations with varying length sequences. This is an important problem, because for my example here, you see that my first event is this much long, second event is this much long, and third event is this much long, right? So this is, this is taking more time. This is the lowest time, and this is the second. Time wise, it is in the second level. Now, if I collect this data, then this length and this length are different, right? So if all these are my observations as a vector, my algebraic space has different kinds of dimensions for 3 different lengths, right? And then I don't know how to compare, because for example, when I want to compare between Euclidean distance, let's say Euclidean distance is a measure to know the similarity between two sounds, but the sounds are different lengths, then I cannot compute Euclidean distance. Correct? So this is a fundamental problem. So there is a dimension mismatch in the time domains, when you handle this time series or spatial series, is the dimension of one portion may not be equal to dimension of another portion. Typically they are equal. They are not equal. So be careful to deal with this varying length of sequences. That means what you want from the varying length of sequences, you project this different time series to a fixed domain. That means find out the feature vector with respect to a fixed domain, and then you compare. You play all your signal processing, statistics, or machine learning games over there. Otherwise, you can't do it. And I can give you one simple verbal example. For example, let's say I say ah, then I say ah, then I say ah. All these are ah. So if I say these, ah, e, o, even myself, different time-wise. Sometimes I say ah, then I say ah. The speech recognition system has to understand this is ah. Okay? And how it will know that? Because it's different time lengths. So how it will compare between each other? So you have to bring this whole thing, the comparison purpose or the analysis purpose, you have to bring the whole thing into a fixed dimensional feature domain, and then you do whatever you like. Okay, so that's what I said it here. Why does this fundamental issue arise? Dimension mismatch. If not the same dimension, how do we compute between vectors? How do we compute the distance? This is a practical problem. And the note is that we need to be careful to deal with this time series signal. We need to know how to treat this signal. Okay. Now I show you some examples in the next slide. So I can compare in the original time domain between each other, or I can compare in this, let's say in the spectrogram domain. Okay. For example, I take this portion, and then instead of this portion, I compare this guy, this image, and this image by upsampling or downsampling, I bring it into fixed length, and then I compare between different, let's say, ah sounds. I can do that, right? That's not a problem, because my belief is this, that almost all ah sounds will have similar, frequency profile in the spectrogram when I, project into the power spectrum domain. So now, if I can bring it in the same image domain, then I can use that, you have already heard about the convolutional neural networks, deep neural networks. So when I come to the same fixed length image domain, then I can feed that image to the, deep neural network and try to figure out what is this class of that sound, like whether this is ah, e, or o. It's not a problem. Okay, but that I could not have done here, because my length sequences are very different, and it's too many samples to handle. Yes. Yes, that will happen. Yes. So the approach is that you have a window, and then you shift the window, find parameters of this windowed signal, and then use as a two-dimensional sequence. This is the typical way to handle this kind of time series, a time varying time series. Why I'm using the word time varying, this I have not explained to you before so clearly. Time varying means, you see that if the time varying means some parameters of this signal is changing. So here the frequency parameters of the signal is changing with respect to time. Do you see that? That, for example, here these are the most dominant frequencies. Then here this is the dominant frequencies. You see now more or less 3 band. There is a low pass band also very clear, like this. And When I have a power spectrum is nothing but actually it is nothing but second order second order statistical parameters of the which is the Fourier transform of autocorrelation values. So you basically assume for this particular small portion of the window, this is a second order stationary signal, and then from there you do these analysis. So you see that the second order statistics of the signal is changing with respect to time. That is the time varying means. So here I am showing you second order statistics of the signal, but for other kinds of signal you may have other kinds of coordinates. The bottom line is or in a nutshell is that your some parameters of the signal is changing with respect to your visible coordinate. Here the visible coordinate is time. It can happen over space. Okay, so with respect to space, certain parameters of the signal is changing with respect to space. Hope that now I have understood. I hope that you have understood this what is called varying. Okay, I told time varying, but it can be space varying. So the message is this: given a signal, we have to figure it out from our domain knowledge how to have suitable time sequence for our intended application. So for example, I see something, but I want to figure it out something. I have some inference task. Now I see some kind of observations. You have to transform the observation in such a manner such that your intended task can be handled. Okay. And this is a very important point to learn and to be expert. Otherwise, you can't use it. Okay. Now let's say that I go to a standard problem setup for for the general tools. Let's say the observation sequence. What is the observation sequence? I'm writing here X bar. X1, X2, X small t are basically time points up to capital T. Okay, so I have a capital T length sequence, and now I have taken a multivariate sequence. That means every time point I see a capital K dimensional feature. Okay, so capital K dimensional signal. And this x1 to xk can be, for example, pixels of an image. It can happen. It can happen something else. For example, I can have the first dimension x1, x12, x1t, maybe temperature. Second dimension may be humidity. Third dimension may be, euro values. Fourth dimension may be, what is the prices of rasagollas here? It can be. And then from this, I would like to, predict something. For example, let's say, last in the second class, I was telling you what is the people's mood over time. Then I try to predict what is the people's mood over the time. It can happen. Okay, so I can have very, very different, features here. It need not be image or pixels. Image pixels means all of the things are similar quantity, right? Similar, same dimensional quantity, right? But it may not be. It may be very arbitrary. They may not be, not even intuitively connected between x1 and x2. Got it? So this x bar means that I have, these feature vectors are coming from a process, and I am seeing up to capital T length sequence. And we have to predict a target sequence in our terminology, in machine learning terminology, that is called target sequence. Target sequence is also y bar. I have y1, y2, y t, and y capital T. Please note that there is a corresponding. So x1 corresponds with the y1, x2 corresponds with the y2, like this, okay, time-wise. And that is also a vector I'm using for the, for the general case, that this is nothing but L length target. For example, the first coordinate may be people's mood. Second coordinate may be, what is the price of the potato? It can be, okay, anything that what you think is your useful targets, and that can be multiple targets together. Okay. So for example, you can also happen, it can also happen some values you want to regress. That means it's a real values that what you want to predict, and some values may be some kind of classification problems. For example, y1 can be whether the sequence is a whether this video sequence leads to solar flares or not. Okay, just now somebody was talking in our workshop, right? So first coordinate maybe at this point of time I predict that solar flares will happen. So then this is 1, this value will taken 1, and second instant maybe this is not going to happen, then the value is equal to 0, because I have only 2 possibilities, 1 or 0, right? Flares will happen or not. Okay. But then with that one I have a y21, maybe that's a different thing, which is the real value. For example, something else. Okay, so you can have that kind of scenarios too. So without loss of generality, you assume that x bar is a multivariate input and y bar is the multivariate output, what I want to get from the system. So we have k dimensional input and l dimensional output. Okay, so this is your observation sequence and this is your target sequence. And here I have given you, some kind of ideas that what can be the values of the x. X can have 2 coordinates like wind flow and temperature, and y has 3 coordinates, maybe y1, y2, y3. Y1 maybe I would like to predict what will be the sunshine, how much sunshine will be there, how much raindrop will be there, what will be people's mood. Okay, by seeing the inputs, wind flow and temperature. Okay, it's a valid problem. Now let us come have this kind of sequence. Once I define these things, that means this I observe and this I want to get, okay, from a sequence. Then let us have the tools. First one is vector autoregressive process. What is a vector autoregressive process? I'm reminding you the problem setup again. Given an observation sequence x bar like this, we have to predict a target sequence y bar. Okay, this is the task. And can you construct an autoregressive process model? Autoregressive process model means what? This is a prediction example. In this prediction example, let's say this is my general setup, but in this prediction, in this general setup, I would like to fit a prediction model. In the prediction model, what we try to do, let's say that I am there in the time point t right now. Right now, I have seen all the observations x1, x2 up to xt, and I want to predict what will happen, the value of xt plus 1. Got it? That means in that case, the prediction is like this. I'm seeing wind flow and temperature up to time point t, and I would like to know what will be the wind flow and temperature in the next time instant t plus 1. I'm saying t plus 1, but that need not be. It can happen that what you are interested, what will happen after t plus 7, t plus 50. It's up to you. Okay. So in this case, let's say that means what will happen in this problem, in the prediction problem. I told you that I have a correspondence between xt and yt, right? But that means the yt which I want to predict is nothing but xt plus 1, right? Correct? So in this problem setup, once I bring the prediction problem, that is nothing but I basically treat my yt equal to xt plus 1. That's what I treat. Now comes, how do I have the general prediction equation? General prediction equation is that at any point of time, when I want to predict my yt, that the prediction outcome is yt tilde here, that is nothing but, according to my problem setup, that is nothing but xt plus 1 tilde. Tilde is the estimate or the output which you are getting from the system which you are engineering, okay, which you are developing. So that one, that you want to predict, given what? Given all the data points x1, x2, x3 up to t that you want to predict. So but you do not want to use all of them. You are saying that, okay, I believe that my just previous p samples are more important than all than further samples in the past. So you basically take all the p samples. That's why I write xt minus I. This is a set, and the set has I equal to 0 to p minus 1. So I equal to 0 means xt minus 1, xt minus 2, like this, xt minus p plus 1. That is the total p numbers of past samples. All these samples I took, and then I designed a function f theta. Okay, this f theta is the regression function, some kind of prediction function that basically predicts my yt tilde. Okay, in case of autoregressive process, this is a linear function. That means I take all these xt minus I, and then I multiply with a matrix ai, and then sum over I equal to 0 to p minus 1. Is it clear? This is nothing but a linear combinations of all these xt minus I. And as this is a linear combination, that's why I'm using a matrix ai. Matrix calculation is little bit complicated. If somebody has difficulty to handle ai matrix, the person can use ai scalar. A scalar into vector is nothing but the scalar goes everywhere product with all the vector components, right? So you can treat this small ai if you want. But for the general case, as I have a vector prediction problem, I should have a matrix into vector such that the total product is a vector, right? And sum over all those vectors for this, all these p numbers of past samples. Clear this one? Okay. So if this is the problem, then I must have to know these ai values. Otherwise, I can't figure it out, right? That what is this yt tilde? This is my model, and I have to know what is my ai values. How do I figure it out, those ai values? The thing is very simple. You have the sequence, xt yt, and yt you have defined like this. For a capital T length of sequence or up to t whatever, you basically have this yt minus for all t, yt minus yt tilde, whatever all t's you have observed, you basically have a, this is the fit, right? This is the true data, and this is the predicted data. You want your prediction should be as close as possible to the true data, correct? So you are calculating the difference, that is the L, taking let's say L2 norm of that. That is the standard norm. And then sum over all t which you have observed. Got it? So I know what is my yt equal to xt plus 1. That's the way I will define. What is my x tilde t plus 1? I already know this is ai xt minus I. So can I write like this? Is it okay? That norm of xt plus 1 minus this guy, sum over I equal to 0 to p minus 1 ai xt minus 1 square, and sum over all t. So this is my loss function. Yes.
So the efficiency of the prediction, is it sensitive to capital T?
It's sensitive to capital T, yes. Because if the capital T is very short, that means your number of this kind of samples are lower, right? And if you have too many parameters to learn for that one, you are in a problem. So capital T, of course, matters. At the same time, please note that when I have a time varying sequence, which is generally natural, okay, many cases it happens, then if you believe that my capital T is very large and you learn the parameters for the whole sequence, actually you are basically treating the sequence as a static signal. That's wrong. Okay, so in that case the idea will be a little bit different. That means that for every small windowed sequence or small snippet, you reduce the number of parameters to explain that signal, okay, and then you move it over the time. In general, the capital T has to be more than P, yes, of course. Otherwise, the system is even underdetermined. Now, once I have this L2 based, simple loss function, so my optimization problem is what? Optimization problem is these loss functions I minimize to learn my parameters AI. Okay. Once I know my AI, I'm done, because in that case, that is my, Once I minimize this L loss function with respect to AI, then I will get my optimal AI star, right? So that I fit in here. Now I know my AI star. At any point of time, if you want to know what is my predicted value, I put that AI star, previous values, multiply, I get my predicted value. Clear? So in case of let's say I go back here, in case of this Swedish currency, this one, let's say that my let's say up to this much the time sequence is available, up to October 26 2000 October 26, let's say. Okay, and then somebody is interested to predict what will happen on October 27. So this much is available to the person. So for up to this much, the person figures it out, what is the optimal prediction coefficients, right? Because that is the only data available to him or her, to the person. And then once the person gets it, then he knows all the optimal coefficients. He takes previous some past values up to which he finds out, he or she finds out this is most important. That you have to little bit experiment and figure it out. You take different kinds of p values and check that how much good prediction fit you can have, something like this. And then once you have that, then at this point of time you can predict what you expect as a linear combinations of the past values to the as the predicted value. Am I clear? Okay. So now in this case that I have already told you that this problem when I was telling in the second class, this problem, like this is an L2 norm and this is a linear problem, it's a convex problem. It's a strongly convex problem even. It has one global optimum solution. Okay. In this case, this is a minimization problem, so there exists one global minima of this loss function. Okay. So it's a very stable solution. So once we know the parameters of this model, then we use for any future prediction. Straightforward. Now let us progress further about some interpretability of this model. The future prediction is nothing but a linear combinations of the past signal points. Okay, I have used matrices as the linear combination as the as the extreme case, but you can use some structured matrices, some diagonal matrices. You can use one scalar. One scalar is nothing but the matrix means A into identity. Okay, so you use as you like. Now, if you see this model, what basically I treated? I treated xt plus 1, this is yt, and this is my error signal. Error signal is this yt tilde is the prediction signal. So the prediction signal means that using the past samples, what you are able to predict, and the error is the part that which you could not predict, right? It's clear that the error is the part which you could not predict. Yt tilde is the part which you could predict, right? So I can see this one, if I use this model for certain signals, I can see this one as a generative model. Generative model means what? Any point of time, my true value xt is nothing but this part sum over I equal to 0 to p minus 1 ai xt minus 1 minus I. So xt minus 1, xt minus 2, xt minus 3 like this up to p past values. If you linearly combine them, that is the part which you could predict about xt, and then the extra part, that is this ut part, that is nothing but a driving noise of the system. Okay, that's the innovation. It's also called innovation of the system. Okay, so that is the part which you could not predict in this model. And this one is nothing but a recursion. Okay, it's a dynamical model which basically recursively generates your xt, right? xt plus 1, xt plus 2 like this, correct? And here this part is the uncertainty part or innovation part, noise part, which basically driving the system to generate the samples. Clear? So once I fit this model, I have an idea that how this time sequence got generated out of my model. And then I basically try to interpret my generative procedure. So what kind of matrices this is, okay? And using these matrices, can I, figure it out something more? So these are very, important parts that, this game of generative models. And last day I was telling you the generative model, but there I have given you more importance to the neural networks. But you can see that, it is not the generative model is very, it's not a today's topic. It is there for a long time. Okay, and it can subsume many kind of standard models inside. Okay. So now if you extend this one, this equation, it's nothing but this xt equal to a0 into xt minus 1 plus a1 into xt minus 2 plus dot 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 ap minus 1 plus xt minus p plus ut. And you can choose different kinds of noises. Somebody may say that, oh, I will choose IID Gaussian noise, but somebody may tell, okay, I will choose IID Laplacian noise. Okay? Your noise statistics can be very different. And according to the noise statistics, the generative procedure will also be different. Now, let us consider a fast order autoregressive process for ease of understanding. So you took xt minus 1 only to predict your next sample xt tilde. Now, here I'm using linear function, right? Because it's the linear transformations of the xt minus 1. But can I think nonlinear function? For example, I get my xt minus 1. To predict my xt, can I think this function that which I'm generating? Here I have a linear function f theta, but can I have a nonlinear function? For example, a neural network or something. Is it okay? So I left a question that, say a neural network. So just propose one. You can think many different kinds of functions as you want. Okay. In some cases, you can have a deterministic function. You know that you know the model of the function. Maybe that you want you get this input and then you want a different kind of polynomial coefficients along with sine, cos, trigonometric functions, blah blah. Okay. So I can have a standard construction. Standard construction is like this, that I have an xt tilde that is equal to f theta into xt minus 1. F theta is a function that which I have to define, and that function can be a neural network, can be something else. So if it is neural network, then the generative model is what? That xt equal to the time sequence how it is generating. This part I could predict, and this is the innovation part, right? There has to be something innovation, something uncertain. Because if I do not have the uncertain part, then of course from the previous samples, I can exactly predict what will happen in the next sample, right? And that's a trivial signal. Correct? Okay. So I can have a complicated function of xt minus 1, and then this is the, some innovation sequence. And if this happens, if I do that, where this f theta is not a linear system, then it's a nonlinear dynamical model, and this is a recursive dynamical model. Okay. Now, for all this discussion, mostly I have used that yt equal to xt plus 1 for ease of understanding. That means the target domain and the observation domain are same. That's the way that I have explained it. But for general understanding, we should not have that constraint, because then we cannot handle many systems. So we now proceed where target domain and observation domain are different. You can make it same if you want to for your case, but let's go with the general notations. Now come recursive neural networks. Should I give you a break or something? Maybe that 5 minutes break or 10 minutes break, and then we come back after 10 minutes.
Okay, so like Miss, we will just start with the lecture again now. Please, Dr. Chatterjee, please go ahead.
So am I audible now? Oh, so now we will discuss about recursive neural networks. So let us recall the problem setup. Given an observation sequence X, we have to predict target sequence Y. Now, important concept in this recursive neural network. This is called hidden state inside the system. So what we have this X and Y. So I'm writing this observation sequence X bar here and target sequence Y bar here, and then introducing something that is called hidden state sequence. Okay, please note that the terminology hidden state is a standard terminology, so just mug it up right now. So this is hidden state sequence. This is H bar, H1, H2, HT up to H capital T, and there is a correspondence. That means X1, H1, Y1, X2, H2, Y2. So that's why XT, HT, YT. So it is written, one after another. Okay. Now, what is this hidden state sequence? Where from it comes? So that we have to, we have to understand. So please note that this hidden state sequence is a modeling concept. Okay, it's an engineering modeling concept. It may not exist in the actual system. Okay, so for the actual system, we never know what is the real model. That we never know. Any model that whatever we develop is some kind of a model to explain the signal and the target. So here we are bringing this hidden state sequence for our engineering convenience. So please be careful that it is actually not true that such kind of a hidden state sequence actually exists for the real system. Okay. So the observation sequence, hidden state sequence, and the target sequence. Now the hidden state I can think as an informative feature for our task to have the inference about the target, because I want to go to this Y, right? This is my ultimate interest. I could have gone directly from X to Y. That is typically difficult. So what you do, from X you come to H, and then from H you go to Y, typically. Okay. So this H, you can think it like this. Okay, X was my raw signal. H is a signal which we have generated out of this X bar, such that it basically keeps important information about the target Y. Okay, that's the way to think, and that's why this is you can call it as an informative feature. Can you recall that earlier I told you that given the sequence, you would like to know the gist of that sequence so that that can be used for my inference task, right? So H is such kind of a thing. So this hidden state sequence is a conceptual thing that which we bring in and believe that this is an informative feature from this X, so that information from the X about inside my hidden state sequence H. And so that's why that I will go from H to Y instead of directly going from X to Y. But H will come from X for sure. Okay. So now I also want a recursive system, right? Because being a dynamical system, I want typically a recursive system. So we can bring recursion to have a dynamical signal model in the hidden state domain, not in the X domain, but we try to bring it in the hidden state domain. How? At time point t, the hidden state sequence, hidden state value, ht, is some kind of a function of the previous state, hidden state ht minus 1, and the current observation xt. Okay. Please note that if I have this one, then if I unfold this equation, so check that the at current time ht, this is a functions of the previous state and the current time. But the previous state depends upon the previous xt minus 1, right? According to this equation. That means this current hidden state also depends upon t minus previous t minus 1 and previous previous xt minus 1 and the current xt, and then the previous ht minus 1 is also connected with the ht minus 2 and xt minus 1. So ht minus 2 is connected with xt minus 3. Got it? So in this way, that ht actually brings about information from x1, x2, x, or in the other way around, I better to say xt, xt minus 1, xt minus 2, or a quite,
Yeah.
yes, please.
Yeah. So like, does this H sequence means it just acts as a bridge between X and Y?
Yes. Yeah. Correct. But here, so ht basically keeps informations from xt, xt minus 1, xt minus 2 up to quite long past values. Yes.
Why could we not have defined, instead of using h over here, why could we not have defined it as y of t is a function of y of t minus 1 and x of t?
Okay. So many cases, your yt may not be, because what you do not have the true value of the yt in your hand. Observe which you are predicting. So if I generate my yt as a function of yt minus 1, but the true yt minus 1 I never have, right? So I use an estimated yt minus 1, and that can be noisy, right? So in that sense, that I will unnecessarily introduce noise into the system. That's not a very good idea. Okay. Okay. So neural net. What you do? Okay. So this is I have written here recursive neural network architecture because I am giving the tutorial this part of recursive neural network, but you can think it is a general architecture for a standard recursive system. What it does, it has an ht, which is the intermediate state, which is a function, some kind of a function here. That function input is xt and ht minus 1. Ht minus it is nothing but memory. Okay, in our signal processing terminology, this is nothing but z inverse. Okay, that you put in as a memory value. You get this ht minus 1. You have a okay, that system, it generates ht, and then ht, from the ht you transfer to the target, you project to the target this ht. Okay, and in case of a if I have a recursive neural network, then this is a nonlinear one and this is also nonlinear one. Note that I told it recursive neural network. Some people also called it a recurrent neural network. Recurrent means again this recursive thing. So these two can be neural networks, right? Because neural network is nothing but some kind of nonlinear transformations given some input, right? Here this is the input which is generating this output. Okay, same, this output again nonlinearly transformed and go to yt. It can happen. So this is nothing but some kind of mapping functions. Now let's give some practical examples. ht can be a very simple case that this is basically ht minus 1 xt, they are linear combinations. So that's why that I have this matrix whh into ht minus 1 plus whx into xt plus some bh. Bh is some bias term, okay, in a neural network. But this is a linear transformation of ht minus 1 to xt, and then if this is a linear transformation, then you have a standard recursive system called Kalman filter, okay, which is possibly the most used dynamical model across many fields. Kalman filter. It is also used for localizations of your mobiles or GPS systems to localize for a particular time that you have measurements through the base stations which possibly the Google collects, okay, and then it basically tries to predict what will happen in the next time instant, and then it corrects according to that measurement. Okay, that's the Kalman filter does. Now, so a very simple nonlinear system is that, okay, if I have a linear combinations and then you pass through the neurons of the neural network, that is an activation function. Okay. And your yt tilde equal to some kind of zt, that is then this ht you take, this wzt is the linear transform, bz is the bias term, and then you have the activation function again. So that is basically a nonlinear transform. Okay, it's very simple nonlinear systems, neural network based nonlinear systems. And then you design a loss function because you have to know the parameters, like all these parameters you have to know, right, for designing this system. So you design a loss function that is distance, some kind of distance measure between your true yt from the training data what you have and the yt tilde which you predicted for the training data, right? That you design a distance, maybe L2 distance like L2 norm or something else, and then you sum over all the t, that whatever the samples you have, and these loss functions you on the optimization is you minimize these loss functions for the parameters theta, where theta includes all these WHH, WHX, WZH, and all these bias terms. Clear? What is the problem? Now comes one specific case which basically the physics society did, I think in 70s, 80s, is called reservoir computing. Actually, that particular method we used for our sunspot cycle 25, prediction. I think Dhruva will talk about that, and Anubhav was also part of that. He implemented those algorithms. So in this case, what their basic idea is that I have this system. In this system, WHH, WHX, and BH, these parameters are not learned carefully by minimizing the optimization cost. They are random parameters. The random matrices. What matrices? Because you can keep the application one, random matrices are good codes. I mean, this is given by Shannon's information theory long back. So random matrices can keep the informations of the signal pretty well. This is known. Random matrices, IID random matrices are good, columns of that or rows of that are good codes. Okay, typical codes. So they have used this, random matrices means you basically draw this one, the elements of that from an IID Gaussian source or IID uniform distribution. Once you've drawn it, then you fix it. Okay. And then that these things are not learned, only this thing is learned. In that, this is the least square problem. So you have a global optimum solution for this WZTH for fixed value of these WHH, HX, and BH. Okay. And random codes are good because whether I implement or you implement, we will get mostly the similar result. If, and that large random matrices even show deterministic behavior. Large random matrices, singular values basically have very fixed spectrum. Okay. These are well-known results from random matrix theory. Generally, random matrices are full rank with a probability 1. That means that it is invertible. Okay. So you do not have this problem of singularity. So far we talked about recursive neural networks that have the following aspect. By construction, they may offer note that in this all these processes we have this recursive structure ht minus 1. ht is dependent upon ht minus 1 and the current data input xt, right? And ht minus has a long memory chain, correct, if we unfold it, correct? So in the thought process, mathematically you may think that okay, this captures long-term dependencies between the signal components. That means I'm seeing at time point t, but actually it has a long-term, dependencies. Well, but means, for example, if there is a sudden change in the signal, and that it may not be able to track, and that exactly want, because if this is a very slow change, then the tracking is easier, right? And I want to track those things that where there are typically sudden changes, and that's a difficult problem. Then memory. I mean, I can visualize something like a time-dependent memory. For example, sometimes we may need to forget the past, right? And sometimes we have to keep the memory. And this is actually the way that, how even the, typically the human behavior works, right? Because some of the times I would like to give the attention to my past sequences, past values to predict something. And some of the things I think, oh, this is too trivial, it's not required. And then in the machine learning case, all these things you have to optimize. So please remember, note that here I have used very simple one layer cases, but there is no but use a many multiple layered neural network, a deep neural network here, right? So I can have a deep neural network here, I can have a deep neural network here. But in that case, I have to learn a lot of parameters and then I have to do the gradient search, and possibly Shorangshu has told that there are multiple layers, there is something happens, it's called vanishing gradient or exploding gradient problems. So I would like immunity to vanishing and exploding gradient problems, but that might not be possible by these simple architectures that which we talked about. Therefore, people have come up with some new architectures which are more successful than these in the last last decade actually. This is called LSTM, and it's some other versions. LSTM means long short term memory. So the conceptually it brings dependence on the long memory and sometimes on the short memory automatically. So I will give you a brief explanations that what is the interpretations of this long and short term memory briefly. The is like this. What is this? That I have to generate my HT as the hidden state sequence, but in the generation process of the HT, there are several gates. Gates are some input gate, input modulation gate, forget gate, and output gate. Typically, 4 gates are there in the original LSTM case. There is a nice you can follow the Wikipedia LSTM page, or there is a nice article actually here that which I wrote down. I have taken the picture also from them. So in this picture, this is the construction, because all the things are mainly that how you construct your internal state, internal hidden state, because that is the most important concept. If the internal state you can bring in that the internal state has a long memory or short memory according to the time point and the observations, that's exactly what you want. So in the LSTM's case, they have the most important block is perhaps this cell block. Check that here I have written you the equations here. For example, there are several dummy hidden states inside. These are FT. There are complicated relationship between XT and HT minus 1. Then this is a sigma function, sigma activation functions, that which is giving you FT. Then there is an IT. This is the input get related function. Then there is a GT. which uses xt and ht minus 1, and then is a tan hyperbolic function. Okay, so these functions, how they got these LSTM researchers is, I believe, by their experience and lot of simulations and experiments. Now HT, so the conceptually it means HT is a state sequence, but HT also generated by several sub of hidden state sequences. So here, but HT has another, those are these kind of variables. For example, you see the CT here. CT has also a CT minus 1 and GT. Do you see that in this equation? So CT is also generated. CT is one level by hidden state. Okay, that's why it is difficult to visualize, possibly, and you have to work on it. And these equations, how they come up with, of course, requires lots of domain expertise. In fact, how actually these equations came, I also have difficulty to understand. So multiple times you have to go through it. But the general concept is that your hidden state has also other levels of hidden states. Now look into here. For example, let's say I do not want a long memory. That means what? At a certain point of time, this multiplicative factor will be very, very small. That's what I want. That means whatever it is coming out here, that if it's multiplied, this is the multiplication, and that multiplication is also generated out of this xt and ht minus 1. Okay, but this multiplication, if they've gone very small, then what will happen? This whole chain, this will be very small, h2 will be very small, right? So that means that that means that it's conceptually means you are not bringing in the past values, past memories. On the other hand, these values are higher. That means you are allowing the influence of the past values. Okay, so there is this input gate. Then there is this inside. There is a modulation of this set basically is the core of this LSTM, which tells you that how this extra level hidden state sequence is working. And then you have an output gate, and that output gate is again, okay, I want my HT to be not to influence my target so much, or the coming HT plus 1, HT plus 2. That means these output values, these OT, that when it multiplied will go to very small, this H2 will be very small. Got it? So the sequence of HT, that point of time, which is generating for, let's say, 2, 3 time points, HT got very small. So that HT plus 5, let's say, at time of developing HT plus 5, maybe HT plus 1, HT plus 2 is so small that it is not taking basically to construct my HT plus 5 the influence of the current just previous past 5 values of the HT. So it is not taking any short-term values, but it is taking all the previous values, HT minus 1, HT minus 2, like that. So the functions that what they used, these combinations of functions by which they bring this interdependencies between different long and short time memories, and all these functions, the parameters of it, please note that all these functions are dependent on xt and ht minus 1. Okay, and that's why the original architecture still remain. And I think that one of my slide will tell that. I think next slide I will ask this question to check the similarity. And all the functions, that activation functions, what they use are typically sigmoid and tan hyperbolic, and their functional representations are like this. Okay, scalar wise. So the STM is the cell or the memory. Okay, this part. So the memory cell is controlled using the forget gate, which can reset the memory unit using the sigmoid function. So some parts it goes to 0 and some parts it goes to saturation. Okay. When the things are completely 0, that means it is not basically taking care of all the past values anymore. So that means it's a reset of the new memory. So it is now a short-term memory is more important, not the long ones. And then input get and output get respectively control the information input to the memory. I mean, how the memory is getting input, that is basically also controlled or modulated by these input get. Okay. And from the memory cell, how the hidden state sequence HT that which will be controlled by this output. Okay. And the output HT can be completely by this output get. That's what I told, that in the output get it can gives you very small values and pointwise multiplication. So once you do the pointwise multiplication of small values, this H2 can be very small zeros. So it is not affecting the previous, so it is not affecting more to the future generations of HTs. Okay, so this is the way they bring in the concepts of memory, which is time varying memory as a long and short term. Yes.
So like, could you please explain that why you like choose these functions like NH function and the other one, the
sigmoid function.
Yeah.
You can easily see that, the sigmoid function is typically between 0 to 1. So sometimes this is completely 0 and 1 means you have the full presence. Okay. And sigmoid function is basically, -1 to +1. It's a saturation effect. Okay. But now you see that I have this figure, right? The general figure. There is a recursive system, some system, which basically taking xt and ht minus 1 and generating ht, and that ht you are projecting to the yt. That's the way I have designed it, right? And now you see this diagram. That is the LSTM people should. LSTM architecture is, but you note that this is nothing but everywhere the xt and ht minus 1 is the input, right? So this block is nothing but this block, right? Correct? This is a specific block which they found out after a lot of research, but this block remains general. You may figure it out by your own research something else. And the question can come, okay, why not in the generations of HT, I use XT, XT minus 1, XT minus 1 up to P, like in autoregressive case, I have used P previous values of XT, right? So why don't I use P previous values of XT like that even P previous values of HT, having different values of P. Somebody may, right now P equal to kind of 1, right? So somebody can say that, oh, I will use 10 previous values. You could, I mean, it's not impossible. You could do that. I'm quite sure that the people have tried possibly and not much improvement happened. Okay. But if you can bring in some intelligent combinations of this kind of, choices, and maybe that is better than LSTM, it can happen. So you see that? Can you now compare between these two architectures? And I told that, note that there are two main hidden state variables instead of one LSTM architecture, because I have HT, one layer, and I also have CT, another layer. Because we had this CT equal to something in a product or multiplication CT minus 1 plus something into GT, right? And note that this GT, which you got here, this GT is coming from here, that's also got out of this XT and HT minus 1. So this GT is another level of hidden variable inside. Okay. So there are several levels of hidden variables are acting between each other, but ultimately HT is the main hidden variable outside. Okay. So there is a direct, relationship between these two architectures. only that here the architectures are done in such a manner so that they can bring in this concept of long and short-term memories. And it is very successful today. Okay. For speech recognition, I think many big companies nowadays use that. I think that once you write now in the Gmail and that it predicts some words, right? That's also this prediction also the LSTM possibly is used. Okay, so it's very powerful. Now LSTM has many modifications. For example, people LSTM, its convolutional version. Then one famous is called gated recurrent units. LSTM has many applications: time series prediction, speech recognition, text prediction, grammar learning, handwriting recognition, human action recognition, traffic forecasting, etc. Okay, so traffic forecasting is a very interesting problem. We basically want to know how many cars will be there in which kind of on the map, street map of the city. Okay, every time. Okay, now I tell you the GRU. GRU is possibly today is the most used. So this provides some simplification over the conventional LSTM units, smaller the information flow, and it also introduces a reset gate. So it gives more priority to information from the current time step and less priority of information from previous memory cell. Okay, so it's a similar like thought process that my current sample is dependent upon my past samples more possibly than long memories. Okay, memory of course acts, but still maybe that what I'm seeing now has a more short-term correlations are more important. Okay, so LSTM unit has these 4 gates to control information flow. GRU has now 2 gates to control the information flow. One is called reset, one is called update gate. So this is the schematic diagram of GRU. You still YT is the output you want. You have an XT, and then you have the CT is the internal state, and of course depend upon CT minus 1 and XT. So I'm just showing you the equations. So main difference with the LSTM is that now we have these 2 gates, reset gate and update gate. All other gates do not exist. We have this RT and UT, and they are the functions of XT and HT minus 1. And then we have this CT. This is the fail state, again inside. Okay. CT has this kind of similar recursion, right? And HT equal to CT, and then YT equal to this CT plus this CT is ultimately, or HT is ultimately projected to YT. Okay, this is the total equations. If you really have to understand the meaning of the equations, you have to really go through these equations line by line and try to unfold that one for t, t plus 1, t plus 2, some few more equations, and maybe it will be easier for you to understand. So, can I proceed further with complicated constructions like, instead of these gates basically gives you some kind of interpretations of how, into bringing memory. But let's say that I would like to be completely data driven and do not know, that how to bring in this kind of domain knowledge. Then I will use a directly deep neural networks with many, many layers and fit in there and learn the whole thing if my data permits, right? Question is that if we use the DNNs with many layers here, I can conceptually. Question is then, why do not we use such construction so much? Because still, why people, LSTM and LSTM is little old, but GRU is very new, and these constructions we typically use, but not with very complicated DNNs here. But yes, we can that, or possibly, there are who has done that. Okay, so it's not impossible. Note that so far what I told you, I have never done any probabilistic formulations of recursive neural network. Everything is a point estimate. Everything is an algebraic cost, and the prediction is also a point estimate. But you can do a probabilistic formulations of the dynamical systems, okay, to map these XT and YT. Okay, a probabilistic formulations. You can bring a probabilistic formulations for HT. Okay, and a recursive system too. It's not impossible. So now the homeworks, please go through these links and some reading. You yourself do it at home. I have not told you attention mechanism, but you can have a, you can check the attention from the blog if you want to. So these are the typical. I mean, you can take speech recognition as an example because this kind of things are heavily used and most successful in speech, speech and audio domain, or text to speech, speech to text domain. Okay, highly used. So you can try it, read those papers a little bit and try to figure it out. Okay, how these things are done.
Maybe I missed this point. At some point of time, we brought up the issue that the length of HT and YT need not be necessarily of the same length.
Okay. So this is I think here, right? Here. What I told you that the original signal which you are seeing, that for example a speech signal, a time series, that length can be different. But your X, once you define the things, your feature vectors and everything, then it came to the same dimension. And X and Y has to have this time correspondence, typically, okay? So for example, if I have a capital T length observation, then my Y is also capital T length target.
The dimensions of the X and Y did not be the same.
No, it is not. Because Y can be completely different things. For example, here I am showing. Yeah, for example.
I'm asking with this calculation, there should be a 1-to-1 percentage between every element of
Typically, yes. But you can think all Y1 equal to Y2 equal to Y3 dot 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 equal to YT. For example, I have the time length, time sequence X, and I would like to know what class it belongs to. That means everywhere the Y1 equal to Y2 equal to Y3 like this, right? If this, for example, if this is R or this is E by seeing the sequence of observation vectors. Anywhere, either it has to be R or it has to be E, right? So in that case, the target is not changing with respect to the time. But if this is a, euro to Swedish krona, euro to dollar, euro to Indian currency, let's say that all these things, euro is the input, and now you want to know all these three outputs. That is changing with respect to time, right? So then I need the correspondence.
So, I don't know if I've missed this, but how do we decide H naught?
Okay, this is a good question. What will happen to the in the very beginning, the H naught? So H naught, typically you assume that either 0 or from one independent realization from a distribution. For example, if this is a Kalman filter, you assume that H naught is a coming from a Gaussian distribution.
On to the hands-on session or?
Yeah, I think that you should move on to the hands-on session. It depends upon Anubhav.
Okay.
So I think that he has to tell us how he wants to do it.
Yeah, okay. So, like Ms. Anubhav, means are you like available? So, like, can we start the hands-on like session right now with you? Means is that means all right with you? Means if he's
Yeah, I think
okay.
it's
So
okay. Yeah.
okay.
Yep.
So then, like, means if you'd like to like share your screen maybe to start the process.
Yes.
Okay, sure.
Okay, so hello everyone. Welcome to the second tutorial from my side. But I think today is day 4 on the workshop. So today we have a hands-on session on time series prediction, which is relevant to the just the talk that you heard right now on sequential data analysis. So in this tutorial, what I uh, will be aiming for is that we have an example of where you will learn how to do time series prediction using a data set called Dynamo ESN. This is actually a simulated version of real collected solar cycle data set. So it's a data set where the number of sunspots have been recorded over time. That was a real data set, but this is a simulated or an artificial version of that, which roughly approximates the real data set much to a large extent. So in this notebook, what we'll be exploring is to how we can use different recurrent neural networks for predicting future time values based on knowledge of certain past values. So we observe some amount of data and we consider that as our training data. And using that, how can we predict some samples in the future? That is the idea basically of this tutorial here. Um, in this tutorial, we'll be using, I think, 3 types of networks. Well, 2 broad categories. One will be a recurrent neural network. So we will have variations such as LSTM and GRU. And the other will be a much more physics-driven network, such as an eco-state network, which has been talked about in the tutorial as well. So you can consider that the eco-state network could be thought of some sort of a baseline if you want to compare the neural network models. But in these cases, also the eco-state networks can also perform reasonably well, as we will see. And it's suited also in situations we do not have a lot of data available because effectively we have less number of parameters to learn. So, and this tutorial is based on this neural network library called PyTorch. Hopefully, I think there has been some familiarity with this in the previous tutorial, right? And we mainly use some libraries from PyTorch, and the libraries for LSTM and GRU are taken from them. As you have just seen, LSTM and GRU are just 2 versions of the RNN, which incorporates the features of having a long-term memory, but also solving some problems such as modeling long time series and so on. It's a much more popular and more successful version of the simple recurrent neural network, or as we call it, like vanilla recurrent neural network. So I will explain to you. I think you already have this notebook under the files which you have downloaded on the June 29th session that I also took on Lasso and PCA. So if you downloaded that folder there, you will have this IPython notebook inside that folder. And also you will actually have a data file that is called dynamoesn.txt, and you can I have shared some instructions of how you can upload this to your Google Drive and then load the TXT file from there. Or if you want to do this in locally in your computer, you can also do it in that way as well. But I've provided some instructions here. For this notebook, we'll be using some GPU support just for the ease of computation. Of course, this can be also done without. Just to make it a bit faster, we will use some GPU support. And in Google Colab, the good thing is that you actually have free GPUs available to you. Um, the only caveat is that there's a timeout which happens if it is inactive for certain amount of time. But for this kind of short sessions, it's perfect. So if you actually there is an instruction, if you go to this edit and then notebook settings, you can see that you can choose your hardware accelerator as your GPU. So you have options like non-GPU and TPU. You can actually choose this as GPU, and then once you select and run this command, you'll be able to see the status of your active GPU. So as you can see, this is not run now, but usually you should be able to see that you have certain amount of RAM memory left for your settings. So in any case, um, the first thing which you don't need to do but it's done in the cell here is kind of processing the data. So why processing the data? It's done in the sense that because we have solar cycle data, and I will show you just a picture of how this data looks like. So you can see the data has some oscillations. You can almost like sinusoidal like oscillations, right? So the idea is that each of these oscillations represent one cycle of data, one cycle of solar series data. And I think I have some information of what the solar cycle is. So a solar cycle is actually a periodic changing in the activity on the surface of the sun, and it's of interest to astrophysicists as to when will this next peak in the sunspot happen in the next year. So this is something that happens actually um, very periodically, and one solar cycle corresponds to 11 years of data. So it's a lot of data that's been collected, I think, on a monthly basis. So it's not a huge amount of actual amount of data. So, but this is a simulated data, so you perhaps see a bit more samples here. But the real data will have perhaps even lesser amount of samples. Um, as I explained, that this Dynamo ESN is a one-dimensional time series data that is synthetically generated through simulation. The time index represents months. So whenever you have an index here, this, although I say here as time, this actually represents kind of months. And then the vertical axis measures the solar activity in terms of the number of sunspots. So how many sunspots were detected every month that has been recorded. So here you'll find some instructions to load the data file in the notebook. You can actually put it in your Google Drive, and there's a feature to load your data from the Google Drive in the Colab, and you will actually find this not so difficult. I think there are also examples online if you just search of how to do this. It's not yeah. So it's not extremely difficult to fix this. Once you've loaded your data, we just load the files, and then we do this pre-processing. So what the pre-processing does is that it basically um, obtains your data in this nice format so that you have your solar cycles kind of represented. And then we actually have some more pre-processing steps to make it into a training, testing, or a supervised learning scenario. So a supervised scenario is what? Is in the case that suppose I want to predict this particular um, say cycle of data. That means for this cycle, all the previous cycles of my data are my past observations. So I need a kind of scenario where the network can be trained to look at all or a certain window, not maybe all, but or even a certain window of data, say a couple of samples behind, and predict just the next point ahead. And then again, you look at certain number of points uh, once you progress the window a bit forward, you look at those number of points and predict the next point ahead. This can be either predicting a single point ahead, or it can be even predicting multiple points ahead. So you look like a very small amount of window and you predict the next few couple of points. So this kind of processing is actually done already in these cells, and once you just only need to run these cells to make the data ready. The notebook also has some files to build an echo state network from scratch, but you don't have to build the entire network. Rather, what you have to do is you have to complete some parts of the code which implements the update function of the ESN. I think this has been talked about in the lecture. The ESN is basically, yeah, as you can see, it has a structure of the RNN's update equation where you're updating the hidden state, except that your W rays and your feedback matrices are not learned. These are rather unlearned matrices and rather fixed at random matrices. So you just have to implement the state function, and the output equation which you have, there's a next equation is yn equal to w out of hn. That is the only thing which is kind of learned here. And you can see this as you go to the code, that this output layer, which is the learnable layer here. So the only thing you need to fill up here, I think there's some parts to fill your echo state update. You can go through the notebook to find the parts where I have labeled this as code to be filled, and then you can do that. Let me try to go through this one more. Yes, yes. As you can see, there's a part of the notebook left blank here. So this is the part that you have to fill using the equation and the instructions above. And once you execute this, you can actually have some function to train and predict this, do the training and prediction of using the ESN network. And if you do that, you should be able to see a graph of your predicted output versus your training output. I don't know if I have a figure here, but once you run it, you should be able to see kind of comparison curves. Then the next part of the tutorial is basically doing the same thing using an RNN. Here also you don't have to implement the RNN equations. We have RNN libraries already available from PyTorch to do that. What you need to implement is the training loop in PyTorch. I think yesterday you had a tutorial where you saw how does the training loop works while using convolutional networks or perhaps deep feed-forward networks. It's a similar process, but here you just need to write the code for implementing the training loop in PyTorch, basically. So as you can see here, there's a optimization through stochastic gradient descent, or rather mini-batch stochastic gradient descent. So here, no, I think this is stochastic. Stochastic gradient descent. So here you just have to fit in the parts where you call the network to get your predictions and then update your weights and so on. But these are not huge lines of code. If you know, it's rather small. And then the next idea is actually to use the RNN model for the prediction. So as I explained, when you train the network and when you predict on a new, say, a new cycle, you start with some number of a window of points as your, let's say, a window of history of points to use. And then you use these set of points to predict the next point in the cycle. And once you have the next point, how the prediction works that you use this next point back into your window. So you shift the window by one step and then you predict the next point. So this kind of shifting and then prediction is the operation that I would like you to code here. And this window can even shift by multiple points, depending if you predict, say, multiple points ahead, you can then put those points in the window and shift it by the same number of points. And that's usually how time series prediction works. But not in all of these cases, you'll be getting point estimates. So there's no probabilistic estimation here. It's rather very point estimates, but you should be able to see. So hopefully if your training and all these things work, you should be able to see that your iterations and your MSE loss versus iterations goes down. Here we use MSE loss or mean square error loss as the optimizing loss. So if your training goes down, eventually your losses will go down and as your weights are learned. And then you can obtain your predictions using a GRU model. You can also have a functionality to obtain a test error using a GRU. So you can actually see in terms of MSE quantitatively how good is your estimate, and you can visualize some predictions as well. I think there is an optional task I've also included to do this using the LSTM, but once you do it for the GRU, it's just a matter of choosing the LSTM mode. I already gave you the configurations here. Note that this function or this class that I've defined up here can choose, you can choose either LSTM or GRU by just providing the type of RNN in the arguments of the class. So you
Uh,
can do that.
Excuse me. Anubhav, this is Subhadeep.
Yes,
Uh,
yes.
is there any problem regarding the files that is missing or something? I just come to know about this. In the
Not I don't think there should be a file missing. The only file which is required, I think, is the Dynamo ESN 28.
So that is already shared in the previous
Yes,
disk.
that is already shared in the previous folder. I checked.
Okay. So and the lasso and the other PCA solution, that is also uploaded in the workshop website. So you can find it. People can find it in
Yes.
there in first July material
Yeah.
section.
Yes.
And
Yes.
whatever else is after the tutorial, so the solutions will be uploaded. Okay. So that's fine
Yes.
as well.
Yes. Sure. Yes. So yeah, I think you can just find those files, and in the 29th June notebook, I think in that folder you'll find these notebook and the related files. But the solutions for the previous tutorial are available, as Shubhadeep told you, in the folder that you have for today, it's the 1st July. So yeah, we were at LSTM. Yeah, so it's the same part, just you have to run it for the LSTM. Again, just coding how to obtain the predictions, but this is a similar code that you already do once for the GRU. It's just kind of replicating it for the LSTM. And at the end, you should be able to see that if this was the actual test signal that you were supposed to predict, you will see actually a very decent prediction with the ESN. At least in the first cycle, it's almost tries to follow a lot. Then you see predictions by the GRU and also then prediction by the LSTM. And then you can kind of quantitatively compare using some metrics such as mean square error or mean absolute error and R2 score. I think these were introduced in the first few tutorials of how these metrics work between these test signal and your predictions. So you have some quantitative estimates. And then I have some additional task if you have time and are interested further to explore of trying to change the model hyperparameters of the STM to perhaps improve the prediction or checking the variance of the prediction, and I provided some hints of how you can do that. So that's actually all about the notebook. There's only one notebook for this tutorial. So I think you can proceed and try a bit. And at the end of the tutorial, I will, before the tutorial ends, I will show you a solution of how this is done. And later you find the solution also in the 1st July folder that Shubhadeep will share later on. Any questions or queries? So yeah, just feel free to just unmute and ask if anything is unclear, because I'll be active. Okay, perfect. So is everyone able to proceed a bit or follow? Any questions?
Does anyone have any like questions or comments for Anubhav? He's still here with us. So let me see if you have any thing to ask him or anything to speak to him about. So please go ahead and just unmute yourself and just ask him the question which you'd like to ask. Okay, so like one like quick announcement is that the Miss evening session today would start from 6:15 p.m. and there will not be any session tomorrow.
At least like in the tutorial, how far have you managed to go to? Did you try at least the echo state integral? I think that's a bit simpler compared to the RNN version. And hopefully you will not have problems with loading the files and so on. In the case that nobody has any further questions, Shubhadeep, should I proceed and uh, show the brief solution for the tutorial and then people can try later?
Yes, I think that would be nice actually, because I guess nobody has any questions for you right now. So maybe means if you can just explain how you
Yeah,
are doing this. Okay.
yeah, sure. So this is the solution for, let's see, take some time to load up. So yeah, as I told in the beginning that we just need to do these three tasks of how you are fitting the ecostate network and how you are using the RNNs. But mainly, I'll show you first about how we do the ecostate network fitting. So once you fit the ecostate network here, so you have a class called novel ESN. This is a class living subclass from N module, which means it's a PyTorch module. So it can be trained using the normal PyTorch framework of optimization. So in this one, we are defining the feedback matrix and the residual matrix here. Note that both have been defined using these functions build feedback matrix and build reservoir matrix, which are here. And both of the matrices are actually random normal matrices, which means that these matrices are basically containing independent and identically distributed random variables. So there's nothing to actually learn in these two parameters here. Then this state is recursively computed using only the observation input. So just to implement this equation, which is actually very straightforward, and here I can show you how this is done. This is basically just looking at this equation and implementing like here. So it's a matrix multiplication between two things, and we just add the result. And in the end, you can take a tan h on top of the result to show that it's recursing on that. That's the idea of how you build it. And here it is called x state as your recursion, but that's basically the variable to denote hn here. And once you have done that, I think there is some code to already train the function. So basically, you have your model. That is the only trainable part is the output layer, which is the output matrix here that you initialize using this part, and the rest of the things are untrained, right? So you only pass your predictions to the output network and then compute a loss. This loss is using an MSE loss criteria, and you take one step backward in the optimization. The backward basically means that you compute one step in your backpropagation algorithm, and then you get the weights. That means you get the gradients for your weights, and the step basically updates your weights by using the computed gradients using this optimizer step. So actually the second exercise was just using these kind of ideas. So you just need to know how these things work. In the second exercise, I told you to try to execute your and also before I should show you that how your predictions will look like once you've done that. Once you did the training and the prediction, so you can see that the prediction is fairly close, at least in the beginning for these ones. Now here, as I mentioned, that here you have actually in this toy example, you have 77 solar cycles, and we do this prediction only for the 74th cycle. So we have a data before the 74th, and but we do not take the entire part of the data. We have a window of length 32. So we take 32 number of points, and we use this 32 points to predict 1 point in the 74th cycle. And then using the prediction, put it back in a window, shift the window, and predict the next point. In this way, if I continue the process, I will eventually be able to predict all the 74 points in my cycle data. So this is how you define your model. This was more or less already done in the question. What you needed to do, I think, was just define some missing parts and complete this training loop. The training loop was basically as I showed in the ESN case, using the same idea. You have your input, you pass your model to a forward. This forward basically calls this forward function of the RNN. So it passes the entire sequence to the RNN and then gets the output at the end. So this means that in this case, it will pass this window number of points into the RNN, and the unfolding that you might have seen in the lecture happens implicitly actually inside the RNN. So you don't have to define the update equations as you did in the echo state network explicitly here. The self.rnn, or rather the RNN definition here, has functions inside the library to implement the recursion. So what you just get at the, or what is of interest to you, is this output, and you also actually get the hidden states for different layers in case you're using multi-layer RNN. More documentation regarding this you can actually find in the PyTorch website. If you just type nn.rnn under the PyTorch, you will get what do the individual arguments represent. And then what we do is that once we get the output from the RNN, just like in the echo state network, once we get the output from the recursion, we use an output layer, right? The only trainable output layer. But here in the RNN, not only is the recursion layer also consists of trainable parameters, the output layer also consists of trainable parameters, and we call this output layer as FC. FC stands for fully connected. And this output layer is a linear layer that basically takes the output from your RNN and then maps it to the output size. So this output size could be, say, one sample. It could be 5 samples, depending on how many samples in the future you want to predict. So note that in this case, we don't predict the entire cycle at one go. We predict small number of points and then use those predictions back into the predicting window to continue the process. So once we done this prediction, then the next function was this predict RNN, and this is exactly the kind of operation I was showing with my hands here. This is so that you have an eval input. This eval input will help you to get a prediction. Use the prediction back into your eval input. So you shift your eval input one step towards the right and get your prediction as the latest observation, and then use it to predict the next sample and so on. And then you can continue this recursively to get a full prediction of points. So this is what the RNN, the predict RNN function does. And the important thing to note that since this is a prediction function, in PyTorch, if you do not define this under this kind of block called with torch.nograd, it will it can compute the gradients, which you don't want. Here you want only the function to evaluate, but not compute the gradients or do any sort of learning. So we set as mode.eval, which means it tells the network to set it in the evaluation mode and then run the no grad operation on it. So once you do that, it should be, and it, since as you can see, this is a for loop, so it's a recursive process of the prediction. So once this for loop is completed, you should be able to get the entire set of predictions to compare with the cycle. And then I think I have a plot maybe somewhere here that you can visualize also the predictions which you get using 32 tabs. So the tabs represent the size of my input window, and this is the cycle index. The next step was just to repeat the same process for the LSTM. It's basically the same exercise. You can reuse a lot of the code that you already have coded just to choose the LSTM function and try it and check it out. This was more of an exercise to just see what the LSTM does, because you learned about both the LSTM and the GRU in the lecture. So in the LSTM, you can see that it provides a different kind of fit. So GRU was more fitting a bit on the front and less on this side. The LSTM doesn't fit either edge, but more represents the more of the shape, perhaps a bit consistently. And then finally, you can compare all the four predictions that you had using the ASN, the GRU, and the STM. As you can see, the ESN actually does quite a decent job compared to them. And then you can have some additional metrics for comparing test MSCs. Here also you can see that the test MSC, perhaps GRU performs better. LSTM is not so good because it doesn't map so much on the edges. But ESN is actually very comparable to GRU. So this also shows that in case of, I mean, it's not always that just because ESN is not a deep neural network architecture, it will not perform so well. It can be a common misconception perhaps because of the simplicity of the model, but in this case, rather simple models also work quite well. And the next task was more additional, but you can try it yourself to try and see if you can obtain a better result by varying the hyperparameters, because here I have provided you some hyperparameters which I tried and they worked, but of course you can, this is not extensive. You can actually experiment a bit more and see which hyperparameters can give you the best possible results. So all these, except the, of course, the input and the output size, the number of hidden layers, the number of layers itself, the learning rate, the number of epochs, these are all valid hyperparameters in your algorithm which you can use. So that was it. And if you try this, and you can actually then later on see that you will get a confidence interval for your GRU as well. So you can get kind of deviation of how good these estimates are. Because earlier you just had this one line, right? But here you have the line, but also some more deviation here. And I will share this notebook also to you so you can try and see this part. Yeah, that was actually all. Any questions or final comments? Okay.
Yeah. So then means if you do not have anything to um, ask Anubhav, so then let's like okay. So let's thank the speakers then, and see you again at 6:15 p.m. Okay. Okay.
Yeah.
So then we are just like closing the session right now.
Yeah. Okay. Thank you.
Yeah. Thanks a lot, Anubhav.
Thank you.